Okay, so we've talked about exponential growth. Now we're going to talk about exponential decay. So you know that growth looks like this, and it just shoots up super fast. Decay, on the other hand, we start with something and it's being cut in half, cut in half, cut in half, and it takes a long, long time for it to ever reach zero, and it just flattens out almost completely. So this is the idea that we take something to some power. So we had like, I don't know, some constant. This would be the y-intercept. And then we had some power, so 2 to the x, and it just shoots up like that. Over here, we're going to do the same thing. Now, if we started with 6, but what happens is you have this thing inside here is less than 1. Because if you multiply something that is less than 1 times itself, so like a half times a half, you get a quarter, right? This number is smaller than the original number. And if I take a quarter and again multiply it by half, I get an eighth. And if I take an eighth and I multiply it by half, I get a 16th. So you can see, like, as you multiply numbers that are smaller than 1 times themselves over and over, they get smaller and smaller and smaller. But it's impossible for them to reach actual 0. Unless we talk about like some other outside form of dampening, that kind of stuff. Okay, so that's what we're going to look at, and we're going to put that into GeoGebra just like we did with the exponential growth functions. Okay, so let's go ahead and build a little exponential growth and exponential decay function. So first I'm going to make a slider bar, call it A, and we'll make this go from, let's say, 0.1, because we don't want to go too small, we don't want to go to 0, but our maximum of, I don't know, 5. Actually, we do want to, this is okay. Maximum maybe 2, going by 0.1 each time, and we'll apply that. Okay, so now I'm going to make a function here. F of x equals, so I want to have my variable a go to the power of x. Okay, so, well, when it's 1 to the x, whatever power, it's going to always be equal to 1, so we get this flat line, right? But what happens when we go a little bigger, right? So when we go to 2, we have our classic exponential growth. It's doubling each time. So at 1, it's 2. At 2, it's 4. At 3, it would be 8. So each time it's doubling here. I could go even higher and show you tripling and quadrupling, but I think you already got that. Alright, so now let's go back. What happens? So we're going down, down, down. When I get to 1, that means 1 to any power. So 1 to the 12th power is still 1. So 22nd power, it's still 1. What happens when I go now into the decimals? So anything less than 1, it starts to have what we call exponential decay. And you can see it shrinking there. Okay, so the more, or the smaller the fraction, the more we get to a steeper and steeper curve. Now, let's just for fun, let's go to the negative numbers. What happens? Let's go, how about -2? I don't even know what's going to happen. I can't remember. So go to 0. Okay, so 0 to any power is just 0, but you can't actually take 0 to the 0 or 0 to any negative number, right? You can't divide by 0, so it's not existent in the negative numbers. Alright, and then what happens when I go to negative? Yeah, you can't take negative numbers to a power, right? So they're just not, they do not exist. So interesting. So that's just playing around with that. Now we're gonna go ahead and put in a data set and see if we can match a curve to that data set.